Hello, hi, I am Irene Yoon. I'm a PhD student at the University of Pennsylvania, and I'm going to tell you about formal reasoning about layered monadic interpreters. This is joint work with Yannick at Inria and Steve, my advisor at UPenn. Cool, so today we're going to talk about free monads. They're a data structure for representing effectful programs. Here we consider a computation whose interactions with the environment are reads and writes to a state. Intuitively, you can think of this as a trace semantics or a tree where here you have a program interacting with the environment where the first interaction is a syntactic event where you do a read from a reference cell, X for example, and you have a branching continuation where the first is continued with a result R, and the rest is a continuation with a different kind of event where you do a write to a reference cell Y with different natural number values. So typically in a monad, you have a parameterization, monads are of type to type, where you're parameterized with a result type. However, in a free monad, you're also parameterized by a family of events which describe the operators in a language. So in this example, the type of this would be free memory E, nat, where memory E are the read and writes to reference cells. So given this data structure, how do we actually give a semantics to it? We can give a semantics to it by using monadic interpreters, given this roughly OCaml snippet saying that you have write to a local variable X and a write to a reference cell Y, which should be writing to memory. You can encode this as a free monad that may possibly return a natural number value where you encode the reference cell by saying you have some memory events, and then the local variables are encoded with local events. Now we can give a semantics to this in a layered fashion. If you know how to fold over the structure of a particular free monad, you can have an interp constructor, which folds over a monad, and given a handler that gives a concrete semantics to your memory events, you can then go to a state transformer, which represents memory as a heap, and then you're left with a free monad with the remaining events, which are local environments. Then we can give a full interpretation to the event by giving another layer, which, given that you know how to fold over the structure of a state T applied to a free monad, you can have an interp state function, get a handle of a local environment, and then the resulting monad would be a nesting of some state transformers, and then now you have the remaining free monad with no events left. And at each layer of interpretation, we have a new notion of equality. You can imagine at the OCaml level, you have the syntactic notion of equivalence. Whereas on the free monad, you can have a free monadic equivalence, assuming that you have an equivalence defined for your free monad. And then for the last two monads, you can imagine that you can define some kind of notion of extensional equality, which is an equivalence up to the resulting environment of state. Right. So the goal of this paper is how to actually bring modular reasoning and semantics for such layered monadic interpreters. So just to situate this work, I'm going to give you a bird's eye view on all the related works. This has been built upon a rich tradition of nested interpreters since the 90s, where people have used nested interpreters to give a solution to the expression problem in very popular programming languages such as Haskell. Nested types are very useful. And free monads allow us to use free monads in a total type theory such as Coq. So this particular work is built on top of interaction trees, which is a Coq library with a data structure which is technically a co-inductive free monad. The co-inductive and the freer part won't matter for the rest of this talk. Right, so what is the problem that we're trying to solve as part of the Vellum development team, which is the formal semantics of LLVM-IR in Coq? We've developed a formal semantics for LLVM-IR, a realistic production language, production level language of using interaction trees, which has this layered form of interpretation. So when we do this, we get interpreters at each level, which is extremely useful because, as you can see, this diagram of stack is very complicated, but you can see that the last layer, we can actually give a choice to what kind of interpretation we can give to non-determinism, which we have as our last layer here. And at each layer, there's also a lot of equational theory involved, monad laws, and more. But the difficult thing is that there's a lot of boilerplate meta theory where there should intuitively these structural rules that are preserved throughout the layers of interpretation. So previously, we've identified that the semantics is somewhat extensible, but kind of limited. But the reasoning principles are not reusable, and in this work, I'm introducing that we're going to remove all these extraneous words. So in practice, what this has looked like, in our case study, we've done a simple imperative language to assembly language compiler correctness proof, and in the middle of our proof, we've identified that we've had to continuously apply the same structural rules, but at different layers, which incurs different proof obligations at each layer, and also redundant boilerplate, whereas the key idea is that in our new proof, we can actually identify the structural rules which are preserved throughout interpretation, and we develop the necessary meta theory to do this. So the contribution is that we have a new meta theory to reduce the boilerplate in formal reasoning about layered monadic interpreters, and in the way we also introduce new abstractions of interpretation. And using this, we can do algebraic and heterogeneous relational Benton-style reasoning, which is suited for formalization and reason about program transformations, such as compiler correctness statements. And this is all a COP library that is used extending the interaction trees framework. And if you didn't read all this, the takeaway is extensible meta theory for extensible effects. Right, cool. So kind of going back to the initial example, right? What's the problem? Why do we not yet have the right layer of abstraction? So once we have this free monad, we can say, oh, as long as we know how to fold over the structure of a free monad, we can write an interp function over it. But then once we have a state T applied to a free monad, we have to actually use a different function called interp state, because the way that you would fold over the structure of a state T applied to a free monad is different from just a free monad, for instance. And the idea here is that we need to introduce the right kind of abstraction so that, like, looking at these, this interpretation, we want to introduce a new abstraction so that this last layer really is the same kind of interpretation so that we can lift the structural rules. So how do we build layered interpreters? So the original, this is just the type signature of the interpreter function of the original ITRI library. Given an interpretation function for a given free monad, you are parameterized with an event type. Just to remind you, that's the family of events, that's why it's type to type, that describe the operators of your program, and then a target monad, which is the target of interpretation. So given a handler that can give you a semantics for each of the events in your program, you can take some free monad that has these events, and then interpret it into your target monad. And the problem here is that the interpretation function is parametric in its target monad, but it's not parametric in the source monad. It's fixed here. It's exactly the free monad. So the key idea is that we want an interpretation function that can be layered. So we generalize the notion of a free monad and define something called an interpretable monad, and then we characterize the layers of interpretation using higher order functors. Right. So now we can have a new definition of interp with more things parameterized on the definition. So there's actually two new types that we see here on the definition. We first have a layered type, and then we have an index monad. I'll explain this throughout this slide. So the layer is, morally, a monad transformer and a higher order functor, which lifts the boilerplate meta theory. And what we call an interpretable monad is the now newly parameterized source monad, which is a layered index monad that can trigger events, which I will explain. So given this last layer of interpretation that we've seen earlier, concretely, the type of layer will be the state transformer with the state of heap, and then the index monad, which is a higher order functor representing respecting iteration. And the index monad is an index monad with events with what we characterize as having an operation called trigger, which represents a monad that has a minimal impure computation for performing an uninterpreted event. And then the target here is a state T transformer applied to the free monad with no events left. So the layered domain should respect the necessary structural rules. Right. So now that we have a new abstraction for defining the interpretation function, how do we actually get an equational theory that can compose? Right. So relational reasoning on monads is not new. The most common laws, or the monad laws, as we've seen in the previous talk, where you have the expected left unit, right unit laws for the return operator, and the bind operator is associative. And we introduce a relation called equivalence modulo R, or called EQMR, which is an equational theory for monads with a parametrized relation R. So this not only generalizes the monad laws, but it offers a relational programming logic for monads. So in practice, we can reason about program transformations with postconditions on the resulting values, where that R is your postcondition on the resulting values. Furthermore, we have some structural laws that we've characterized this equivalence to hold. So in order for this to be a useful equational theory, there are some expected laws, such as monotonicity over the parametrized relation. And if the relation that you're parametrizing over is a partial equivalence relation, the resulting EQMR will also be a partial equivalence relation. And then also the relations composed in a somewhat expected manner. You can find interpretation laws and inversion laws and lifting laws for monad transformers in the paper, if you are interested. So this kind of parametrized relational reasoning, I just wanted to show you a couple more rules, are nice for kind of having this kind of heterogeneous reasoning about program transformations. So you can do reasoning on pure values, where if you were to want to relate a monad that returns an element and with another monad that returns an element, this should be related when the related results should be related to each other. And it's heterogeneous in the sense that A1 and A2 does not necessarily have to be the same type. So it can be monads returning different values. And then we have the bind closure property, or if you're more familiar with the logic side, like this is like basically a cut property for bind, where we can relate two monads, which are binds of MA1, K1x, MA2, K2x, related on postcondition RB if we know that the prefix is related under an RA, and the continuation is related by postcondition RB for all related values on RA. So as a result, we have a composable equivalence for layered monads, and we say that each monad can have a particular notion of equivalence with all these structural properties. And additionally, the structural rules for iteration and interpretation should be preserved. So that rule is basically saying interp is a monad morphism that commutes with bind, and then if it's an interpretation of a return, that should be equivalent to a return. And then this is kind of the expected behavior of what it means to be trigger. And to remind you of the definition of trigger, trigger is the minimal impure computation of an interpretable monad. And these laws compose in the sense that it's unnecessary to introduce a new definition of equivalence and prove new structural rules for every combination of layered interpretation. So in conclusion, we introduce an extensible meta theory for extensible effects. And in the paper and the artifacts, we got the badges. We have a Coq library built on top of the interaction tree framework. And we also, this I did not talk about during this talk, we have a generalization of automatic injection of handlers with combinators called sub-event and over. And we have various instances of the equational theory of monads and monad transformers, including like state, error state, and the weak and strong bisimulations for interaction trees, etc. And then the characterization of interpretable monads respecting the theory of iteration, and a novel notion of an image of a monadic computation, which characterizes the domain of a monad, and then a case study, which is an M2ASM compiler correctness statement. And this is kind of a sort of a diagram of the type class dependencies in this project, and the green part is the new part that is part of the artifact, and the red part are some of the dependencies from the interaction trees library. Thank you for listening. I'll take any questions.